Hey, hello, and welcome to our third Thursday webinar. I am Tom Sandry, and as Matt had said, today we're going to talk about benefits of battery testing, how to perform the capacity test. So, let's get started. Now, battery capacity testing is an essential part of battery maintenance. But how do we do it effectively? And did you know that there are different styles of capacity or discharge tests depending on the application of the batteries that are under test? Now, how does a constant power test that's performed typically on a UPS system differ from a constant current test that may be performed on a substation battery bank? And also, there are three basic types of battery discharge or capacity tests that we will be discussing in today's webinar. They will be the acceptance test, the performance test, and the service test. Now, acceptance and performance tests are tests of a battery's capacity. The service test verifies the battery's ability to meet its duty cycle. Alright, before we get too involved in discussing the tests, let's first familiarize ourselves with the terms and the definitions associated with battery testing or capacity testing. First, capacity. The term used to describe a battery's ability to deliver current is its rated capacity. Manufacturers frequently specify the rated capacity of their batteries in ampere hours at a specific discharge rate. For example, 22 amps for 8 hours would be 176 ampere hours of capacity. Battery capacity varies with the discharge rate. The higher the discharge rate, the lower the cell capacity. Lower discharge rates result in higher capacity. And the rated capacity for lead-acid batteries is usually specified at the 8, 10, or even 20-hour rates. We typically see this on the datasheet as C sub 8, C sub 10, or C sub 20. Now the next term is ampere hour. The ampere hour is the quantity of current the battery can deliver. Ampere hour is typically used in applications that require moderate current discharge over long periods of time and is expressed as a certain rate down to a certain end voltage. For example, 190 ampere hours at an 8-hour rate to an end voltage of 1.75 volts per cell, and is typically specified at a given temperature, for instance 25 degrees Celsius or 77 degrees Fahrenheit. Now as an example, let's say that we had a model number MCT2-4000. Well, based on this model number, it will provide 500 amps for 8 hours, or 500 amps times 8 would be the 4,000 amp hours that we see in the battery's model number. Now, another commonly used term is watts per cell, or WPC. The watts per cell is the quantity of power a battery can deliver. The measure of watts per cell is typically used in applications that require a high power discharge over a short period of time and is expressed in watts per cell down to a certain end voltage at a certain rate. Again, for example, 23 watts per cell at a 15-minute rate down to an end voltage of 1.67 volts per cell, again at a given temperature, 25 degrees C or 77 degrees Fahrenheit. Now, this is common in UPS applications. The battery provides short-term ride-through power until, for instance, a generator kicks in as the new power source. Another term that we see a lot is end voltage. In batteries, the end voltage is the prescribed lower limit voltage at which the battery discharge is considered to be complete. The end voltage is usually chosen so that the maximum useful capacity of the battery is achieved. The end voltage is different from one battery to another, and it's highly dependent on the type of battery and the kind of service in which the battery is used. A completely discharged lead-acid cell has a potential difference of about 1.75 volts, depending on the rate of discharge. Now, end voltage is also sometimes referred to as the final voltage, or also it is referred to as cutoff voltage. All right, now let's look at the term float voltage. Float voltage refers to the voltage that is applied continuously to a cell to maintain the cell in a fully charged condition. The proper float voltage depends on battery chemistry, construction, and ambient temperature. Low float voltage equals not fully charging. Therefore, the battery can't supply full capacity. An undercharged lead-acid battery can lead to failure due to a phenomenon called plate sulfation. A high float voltage equals overcharging. Continuous overcharging cooks the battery and elevates the temperature of the battery. Too high a float voltage can lead to failure due to grid corrosion or thermal runaway and dry out in sealed cells. All right, float current. Float current is the DC current that flows through each cell while they are on float. It is created due to the interaction between the float voltage and the cell's internal resistance and is supplied by the charger. A high float current can be a precursor to thermal runaway in sealed cells. Excessive float current can be caused by short circuits, ground faults, or a high float voltage. Now, SOC is the acronym for state of charge of a cell or battery. Keep in mind that a battery that is charged means nothing about supplying load as designed. For example, your car battery is charged, but it will not provide enough current to crank or start the engine. So fully charged is important, but says nothing about capacity. Specific gravity is an indicator of state of charge, or an open circuit voltage test can be performed on sealed cells in order to provide an indication of state of charge. Now, specific gravity is the ratio of the weight of a solution to the weight of an equal volume of water at a specific temperature. Specific gravity is used as an indicator of the state of charge of a cell or battery. Specific gravity measurements cannot determine a battery's capacity. The specific gravity decreases during the discharging of a battery to a value near that of pure water, and it increases during a recharge. The battery is considered fully charged when the specific gravity reaches its highest possible value. Now, specific gravity readings are not required as part of a normal maintenance routine for nickel-cadmium batteries, as we see referenced in the IEEE standard 1106. All right, the next term we'll talk about is equalized charge. Charge applied to a battery which is greater than the normal float charge and is used to completely restore the active materials in the cell, bringing the cell float voltage and the specific gravity of the individual cells back to equal values, is known as the equalized charge. In essence, it's a way of trying to force the sulfates off of the plates and have them reaccumulate into the electrolyte. All right, now let's talk about depth of discharge. Depth of discharge is the amount of energy removed from a battery. It is expressed as a percentage of total capacity of the battery. Depth of discharge is critical to battery life. A battery can generally withstand a much larger proportion of shallow cycles. As an example, 100 cycles to a 5% depth is less harsh than 5 cycles to a 100% depth. Now, we should also understand the difference between series and parallel connections. A series connection is made when connecting from a positive terminal on one battery to a negative terminal on another battery or cell. This is typically the connection that we see within a battery string. In a series connection, the cell voltages will add, but the ampere hours will remain the same. For example, as we see here, 4 12-volt 25 ampere hour units connected in series would result in 48 volts, but still 25 ampere hours. Now, a parallel connection is made when connecting from a positive terminal on one battery to a positive terminal on another battery. Now, in a parallel connection, the ampere hours will add, but the voltage will remain the same. So, for example, as we see here, 4 12-volt 25 ampere hour units connected in parallel would result in 12 volts, but now we would have 100 ampere hours. And remember, battery configurations may have series strings that are paralleled. So the series string would build voltage value, paralleling the strings would expand or extend capacity. All right, now let's talk about the acceptance test. An acceptance test on the battery capacity should be made at the manufacturer's factory or upon initial installation. The test should meet a specific discharge rate and duration relating to the manufacturer's rating or the purchase specification requirements. New batteries may have less than rated capacity when delivered. Unless 100% capacity upon delivery is specified, the initial capacity of every cell should be at least 90% of rated capacity. Now, this may raise to rated capacity after several charge-discharge cycles or after a period of float operation. And we see this statement made in the IEEE 485 document. The performance test. A performance test of the battery capacity should be made within the first 2 years of service. It is desirable for comparison purposes that the performance test be similar in duration to the battery duty cycle. Batteries should undergo additional performance tests periodically. When establishing the interval between tests, factors such as design life and operating temperature should be considered. It is recommended that the performance test interval should not be greater than 25% of the expected service life. Annual performance tests of battery capacity should be made on any battery that shows signs of degradation or has reached 85% of the service life expected for the application. Degradation is indicated when the battery capacity drops more than 10% from its capacity on the previous performance test or is below 90% of the manufacturer's rating. And finally, the service test. This is a test of the battery's ability, as found, to satisfy the design requirements of the DC system. Trending battery voltage during the critical periods of the load duty cycle will provide the user with a means of predicting when the battery will no longer meet design requirements. If the system design changes, sizing will have to be reviewed and the service test will have to be modified accordingly. All right, before we continue any further, let's take some time to talk about safety and understanding the hazards that are associated with batteries. Now, have you ever attempted to locate the off switch on a battery? Well, of course, there is no off switch. By design, a battery stores energy in the form of electric charge. Each individual cell may hold only around 2 volts, but when placed in a series string, the voltages will accumulate. Typical battery bank configurations found in substations and data centers will be 48, 120, 240, 480 volts, or in some UPS applications, 500 volts and greater. Now, since a battery stores charge, when a battery is charged, it cannot be turned off. Even with the battery charger turned off or removed, the battery bank will store charge until it is discharged. Therefore, when working in a battery room, we are working around energized equipment. Unlike other energized equipment, batteries also utilize corrosive liquids and very potentially dangerous gases. Special care and knowledge is required when you are working on or around batteries or working in battery rooms. Now, among the hazards when working around lead-acid batteries is hydrogen gas. Hydrogen is created when the battery is charging. Now, as the battery discharges, some of the sulfuric acid separates from the electrolyte and the battery begins to form lead sulfate on the plates, leaving the electrolyte in a state of mostly water. This process continues and more water sulfate is formed as the battery is discharged further. Now, when the battery recharges, the lead sulfate leaves the plates and reaccumulates into the water, forming back into sulfuric acid. Hydrogen is created because the cell cannot absorb all of the energy from the charging. Water is electrolyzed into hydrogen and oxygen. And remember, hydrogen is explosive. Okay, corrosive liquids. Lead-acid batteries are in a way a chemical miracle. The active materials are simply lead and sulfuric acid and lead compounds formed through the charging and discharging of the battery. When a battery is charged, additional energy is stored in chemistry changes. When a battery is discharged, energy is removed through the reversal of these chemistry changes. When the battery is fully charged, the positive plate is lead and the negative plate is lead dioxide. The sulfuric acid is the strongest when the battery is fully charged and may be as high as 40% pure sulfuric acid, mixed with 60% water. When the battery is substantially discharged, both the positive and negative plates are converted to lead sulfate, and the sulfuric acid is less than 10% sulfuric acid mixed with more than 90% pure water. Now, sulfuric acid is classified as an extremely hazardous substance, and lead dioxide, and lead sulfate are classified as hazardous materials. Now, when working on lead-acid batteries, wearing a face shield and plastic or rubber aprons and gloves is required to avoid chemical burns from the sulfuric acid. Also, exercise caution breathing around lead-acid batteries if there is poor air circulation and ventilation. Lead-acid batteries can generate toxic gases such as arson and stibine gas. The toxicity of arson is distinct from that of other arsenic compounds. The main route of exposure is by inhalation, although poisoning after skin contact has also been described. Arson attacks hemoglobin in red blood cells, causing them to be destroyed by the body. The toxicity of stibine is distinct from that of other antimony compounds, but similar to that of arson. Stibine binds to the hemoglobin of red blood cells. Most cases of stibine poisoning have been accompanied by arson poisoning, although animal studies indicate that their toxicities are equivalent. The first signs of exposure, which can take several hours to become apparent, are headaches, vertigo, and nausea, followed by the symptoms of hemolytic anemia. Now let's talk about the energized electrical circuit. Each individual cell, as mentioned, holds about 2 volts, but when placed in series, these voltages will add. Some typical battery banks, as we mentioned, can be anywhere from 48 volts, 120, 240, 480, and in excess of 500 volts in some applications. Now, when a battery is charged, as we stated, it cannot be turned off. Even with the charger turned off or removed, the battery bank will store this charge. Therefore, when you are working in a battery room, you are working around energized equipment. Now, since we are working on an energized DC system, we need to ensure that the work that we are performing is justified work as defined in the NFPA 70E or the Canadian CSA Z462. Now, the 70E or the Z462 basically states, energized work will be permitted where the employer can demonstrate that the task to be performed is infeasible in a de-energized state due to equipment design or operational limitations. Now, as we established earlier, by design, a battery cannot be turned off. Now, since we are going to be working around energized equipment, we still need to perform an activity hazard analysis, which could either be part of an energized electrical work permit or simply part of our job hazard analysis. Part of that is going to be performing a shock risk assessment. So, things that we will need to clarify: what is the voltage to which the personnel will be exposed? Based on the voltage exposure, what will be the limited approach boundary? Also based on the voltage exposure, what will be the restricted approach boundary as defined in the NFPA 70E or the Canadian CSA Z462? Also, personal and other protective equipment required to perform the task and to protect against the shock hazard. So if the work is going to be performed in the restricted approach boundary, well, no conductive objects are allowed in this boundary. Therefore, we need approved insulated rated tools, and we have to don electrically rated PPE. Now again, part of our hazard analysis will have to include the arc flash risk assessment. So here, based on the task to be performed, we need to first estimate the likelihood of occurrence of an arc flash incident. Again, we can go to the industry standards such as the NFPA 70E or the CSA Z462 for guidance here. In these documents, for instance, 70E, Table 130.5C can be used for establishing the likelihood of occurrence of an arc flash incident based on the task that we will be performing. In the Canadian document, the Z462, we would find this in Table 2. Now also, what is the available incident energy at the working distance, or the arc flash PPE category? Personal and other protective equipment required to protect against the arc flash hazard, and what will be the arc flash boundary. All of this needs to be established before work can begin. Now, if an incident energy analysis, or an arc flash study, if you will, has not been performed, again, we can go to the industry guides such as the NFPA 70E or the Canadian CSA Z462, and we can utilize what is called the category method for determining the arc flash PPE that we would need to don, and also the arc flash boundaries that would need to be established. In the NFPA 70E, this would be found in tables 130.7C 15B for DC systems, or you would find it in the Canadian document Z462 in table 6B. Now, prior to rushing out to the job site, there is certain documentation that is highly recommended or that we should have on hand. One, the battery manufacturer's data sheet. This is where we're going to be able to find what the discharge rate to various cutoff voltage levels. Also, a completed job hazard analysis that is discussed with all crew members prior to the beginning of the job. And since it is energized work, perhaps we have also an energized electrical work permit documenting our shock risk hazard, our arc flash risk hazard, the hierarchy of controls that are going to be utilized in order to mitigate or eliminate the hazards, and sign off from people in the appropriate positions that they are going to accept any of the risks associated with the battery test. And also safe work practices that are going to define the work, provide a procedural guide of how we are going to perform the discharge test, and again, the hierarchy of control methods that we are going to utilize to ensure safety of the personnel. All right, let's talk a little bit about pre-testing. The load testing or discharge testing is the single absolute test when it comes to the ability to determine whether a battery is going to be capable of supplying the amount of current for the desired amount of time. Before performing a discharge test, however, there are several factors that need to be understood. Now, the battery bank to be tested must be fully charged and not overcharged. The individual cell voltages or specific gravities should be balanced, indicating that all cells are in the same state of charge. Therefore, the IEEE standard 450, which is the recommended practice for maintenance, testing, and replacement of vented lead-acid batteries for stationary application, states that the battery should be equalized and returned to float for 72 hours prior to conducting a battery discharge test. Now note that IEEE standard 1188, which is the recommended practice for maintenance, testing, and replacement of valve-regulated lead-acid batteries for stationary application, states periodic equalizing is not normally required to correct cell unit imbalance. Equalized charging should not be performed unless specifically recommended by the manufacturer. And while the battery is on float, read and record the specific gravity and voltage of each cell and record the values in the inspection data sheet. Take the temperature of at least 10% of the cells and record the average temperature on the inspection data sheet. Now, all connections, intercell and interrow, and inter-aisle must also be optimized to their lowest resistance values. Again, during the discharge test, we're going to be carrying a lot of current. So check the terminal post connection. Make sure that we have a good electrical connection. Check the strap resistances. Again, you want to make the measurement from post to post so that, again, we can measure the connection of the post to the strap. And then simply continue along the battery string. Now, if there are 2 posts per polarity, take 2 intercell readings. For instance, take the leftmost posts followed by the rightmost posts. For button posts, make sure the measurement is taken on the button post itself. Again, because really what we want to see is the connection from the post to the hardware. All right, now let's look at an optional test method that will not only capture cell voltage, but in the process of this test method, we will also capture internal cell impedances and strap resistance values. Now, the test that we're going to talk about as the optional pre-test is the battery impedance test. Hi, I'm Tom Sandry, Director of Technical Support here at Protec Equipment Resources, and today I'd like to take you through the Megger BITE Model 2P. BITE stands for Battery Impedance Test Equipment. Now, the way the system operates is the BITE 2P will actually get connected in parallel across the battery string that we're going to test. So, the unit comes complete with a set of current leads, and then plugging the opposite side across the battery string that we intend to test, similar to the way I have it drawn on the board here. So we'll take the red lead, connect it onto the positive post of cell number 1, and then we'll take the black lead and we'll connect it onto the negative post of the terminating or final cell, as shown here. Now notice that the BITE 2P is in parallel across the battery string, and then the battery charger is also in parallel across the battery string. Now, the way the BITE product operates or conducts its test is the transmitter is going to inject an AC current into the battery string. Now, the combined impedance and combined strap resistances of the battery string should be relatively small in overall value compared to that of the load. Therefore, when we inject the AC current, the vast magnitude of current is going to flow through the battery string, being that this is the lower impedance path as compared to the load. So all current should flow through the battery string back to the transmitter with no carryover into the load circuit. Now, the measurement receiver can be considered to be quite simply a multimeter, if you will. It has the capability of measuring DC voltage. It has the capability of measuring AC voltage and AC current, as well as resistance. The kit also comes with a current reading CT. Just set these down momentarily. The CT will also plug into the bottom end of the gun. And the CT will get connected anywhere within this loop circuit. So most convenient would be connecting it across an inter-tier cable. Now, the way this technology works is the bike transmitter is injecting an AC current. The bike receiver is going to actually measure that current value. The potential guns are then going to measure the AC voltage drop across the cell. By measuring the current and measuring the AC potential drop through Ohm's law, we then calculate the internal impedance of the cell. And that's the value that we're looking for trending. Now it's prompting me to go to jar number 1 and or cell number 1, and it will then take a DC voltage measurement. This is going to be the charge voltage, and then it is also going to tell me the internal impedance. So to make the measurement, we merely go across the battery, trigger the gun, and capture the measurement. So as you see, I had 15.44 volts and 6.59 milliohms of impedance. It is now asking me to take the strap measurement. So I will now go across the interconnecting strap going from jar 1 to jar 2. I'll capture that value. And now it prompts me to move on to jar number 2. And I will continue through the test in this manner, capturing the DC voltage, internal cell impedance, followed by interconnecting strap resistance. As you can see, the test moves rather quickly. And that was a bit of a flashback to a much younger Tom Sandry. That was actually about maybe 12 odd years ago, and shame on you, younger Tom Sandry. I did not see appropriate PPE on you when you were performing that demonstration. I hope you learned something in your older age. Alright, let's get back on to the webinar. Now, test length and discharge rate. The discharge rate for a capacity test should be a constant current or constant power load based on the manufacturer's rating of the battery for the selected test length. As we discussed earlier in this webinar, batteries are rated in ampere hours. For substation batteries, a typical rating is 8 hours. Therefore, if we're to discharge at 12.5 amps over 8 hours, that would equal a capacity of 100 ampere hours. But we could also discharge the same set of batteries at 100 amps for 1 hour, or 50 amps for 2 hours, or even 25 amps for 4 hours, and that would still add up to a capacity of 100 ampere hours. Therefore, when setting up to do our discharge test, how do we determine what discharge current to use? Well, when selecting a discharge rate, we should select a rate similar to the use of the battery. For example, a typical UPS is rated to last 30 minutes during discharge. Therefore, we should select a discharge rate that will discharge the battery bank near the 30-minute mark. Substation batteries are rated to last many hours or even days under light load. Therefore, many test companies prefer to use a current of at least 3 hours or greater in order to give the battery bank the best discharge test. Okay, now we have at least established a time period for our discharge test. But again, where do we find the actual discharge rate or load? Now, if we know the ampere hour rating of the battery cells and we have established the time period we wish to discharge at, we can calculate the current that would need to be set on the load tester. But we don't, however, want to assume that the discharge curve of the battery bank is linear with time. Therefore, referring to the manufacturer's datasheet for the battery cells is always highly recommended. Now, the manufacturer's datasheet for battery cells will provide a performance data chart or discharge rate in amperes. The chart will show an end voltage level, the time period to conduct the discharge test, the model number of the specific cells, and the various discharge currents to discharge at to meet the time period and the cutoff voltage. So, using the datasheet that we see here, let's perform or let's set up for our constant current test. So, what constant current rate would we use to discharge the model 2CC-7 type cells to an end voltage of 1.75 volts in 3 hours? Go ahead, take a moment and type your answer into the questions pane. Alright, to use the datasheet and to have given your answer, we first have to identify the 2CC-7 model number, and then we can go ahead and once we've established the model number, the time duration of 3 hours that we gave in the example, and we see that our current would be 38.6 amps. All right, let's do a similar exercise now for performing a constant power discharge, perhaps on a UPS system. So here, what constant power rate would we use to discharge? And let's go with the model HX80 type cell, and we're going to bring it down to an end voltage of 1.67 volts per cell, and we're going to do it in a 15-minute duration. So again, go ahead use the data sheet given to you here and type your answer into the questions. Again, to use the datasheet, first simply identify the HX80 model and then the 15-minute column, and we would see that we would be discharging at 80 watts per cell. All right. Let's move on now and let's talk about connecting a temporary battery bank. All right, do not disconnect power to DC loads if at all possible. If it is required, make sure that the appropriate people are aware before disconnecting the DC. Verify polarity when attaching two DC sources together. During maintenance or replacement of batteries, care should be taken to avoid removing the 125 volt DC from the DC loads. Some sites have DC undervoltage relays that will operate on a loss of control power. Other sites may have relaying that will operate on a loss of communication with the site. If you remove the DC power, you have also removed the protection that those devices provide. If an event were to occur, it would be much more damaging. If the battery charger is a filter eliminator type, it should be able to float the system while changing the batteries by itself. If it is not a filter eliminator, it should never be used to float the system without a battery attached. The non-filter eliminator chargers have an increased AC ripple that can damage the power supply on the DC powered equipment. Now, when connecting a temporary battery bank to an existing battery bank, great care must be taken to ensure correct polarity. You should always use a disconnect switch. Then connect the temporary battery bank with the disconnect switch open. Then measure the polarity at both the top and bottom of the disconnect. Both measurements must be of the same polarity, and this should be done all the time when performing the test. All right, now let's talk about performing and monitoring the test. After the temporary battery bank has been connected in parallel and the polarity has been checked, close the disconnect switch and then disconnect the battery to be tested from the charger and any other load. Start the discharge test at the test current that had been established. During the course of the test, continue to monitor the individual cell voltages in order to identify any weak cells. Make sure that you record time that any cell falls below the end voltage. The test should be stopped if any cell on a lead-acid battery falls below 1.5 volts. For NiCad batteries, the test should be stopped if any cell falls below 0.7 volts. Now, the test can be interrupted and the weak cell can be jumped out and the test can be resumed. If many of the cells are falling, it is best to end the test and recommend replacing the battery bank. Excuse me. Now, let's talk about capacity test methods. There are two methods for battery capacity testing that are recognized in the IEEE 450 and the IEEE 1188 standards. They are known as the rate-adjusted method and the time-adjusted method. Battery capacities determined by the rate-adjusted method are correct for all test durations. However, this method is more difficult to apply than the time-adjusted method. Typically, for tests greater than 1 hour, it is preferred to use the time-adjusted method. The rate-adjusted method is used for test durations that are less than 1 hour. For tests of 1 hour duration, either method can be used, but as mentioned, the time-adjusted is typically used due to its simplicity. Now, let's first look at the time-adjusted capacity method. When using this method, no correction of any type is required prior to the performance of the test. This method can be used with acceptance tests and modified performance tests and performance tests that have a duration of 1 hour or greater. In the previous version of the IEEE 450 standard, the discharge rate for the time-adjusted method was adjusted for temperature prior to conducting the test. This previous method is acceptable. In the current version of the IEEE 450, the temperature compensation method is revised to apply the temperature correction to the capacity calculation after completion of the test. When using the time-adjusted method, the timed capacity is determined through the formula or through the equation shown, where T sub A is the actual time of test to the specified terminal voltage. T sub S is the rated time to the specified terminal voltage, or the published time that we would see in the datasheet. And K sub T is the correction factor for the electrolyte temperature prior to the start of the test. So, let's go ahead and let's say that we have tested the 2cc-3 type batteries, and we used a 1 hour discharge rate on these. So, let's assume here we have our formula for the time-adjusted capacity method. The temperature, let's assume to be 28 degrees C, and let's say that this cell reaches cutoff in 55 minutes. And again, remember, our rated time is 1 hour, but the cell reaches cutoff in 55 minutes. Using the time-adjusted method, we use the 55 minutes divided by the 60 minutes times the temperature correction factor, and we would see that that cell is at 89% capacity. Alright, now let's take a look at the rate-adjusted method. Now, the time-adjusted method is acceptable to use when discharge times are greater than 1 hour. The time-adjusted method does not take into account changes in battery efficiency with discharge time. As a battery is discharged in a shorter period of time, it loses efficiency. Therefore, when dealing with shorter times or shorter test times that are under 1 hour, it is more efficient and more accurate to use the rate-adjusted method. Here, we evaluate the true capacity and not the inefficiency of being discharged at a shorter time duration. When using the rate-adjusted method, capacity is determined through the equation shown, where X sub A equals the actual rate used for the test, XT is the published rating for time, and T is the time of test to specified terminal voltage. And K sub T is, again, the temperature correction factor. Now, the rates can be either amps or watts. So again, let's do another example here. Let's say that we are going to, once again, for instance, do the HX25 battery type, and we're going to do a 15-minute discharge. Okay? And again, in order to perform this, the published value would be 23 watts per cell. So, we have our rate adjusted method equation. Now let's assume the temperature is 25 degrees C and the cell reaches its cutoff in 12 minutes. Now remember, the published rate is the 15 minutes, but our cell reaches its cutoff in 12 minutes. Therefore, plugging values into the equation, we would have our 23 watts times our correction factor for temperature. Since it's at 25 degrees C, correction factor would be 1. And the 26.6 watts, which would be the actual, based on the actual time that the cell reached cutoff. Now, you notice on the data sheet, we have to kind of extrapolate a little bit here because we have a watts per cell value for a 10-minute rate. We have a watts per cell value for a 15-minute rate. So in order to go ahead and get the 12-minute, we have to kind of extrapolate between the 29 watts per cell and the 23 watts per cell. And that's how I came to the value of 26.6 watts in this example. When we plug all the variables into the equation, we see that the cell is at a capacity of 86.5%. All right, and finally, let's talk about battery or cell replacement criteria. Now, both the IEEE 450 and the 1188 recommend replacing the battery if its capacity is below 80% of the manufacturer's rating. Minimum time for replacement is 1 year. Physical characteristics such as plate condition or abnormally high cell temperatures are often determinants for complete battery or individual cell replacements. And that concludes our webinar on the benefits of battery testing, performing the capacity test. As always, I thank you for attending our Third Thursday webinars. I do truly hope that they are a benefit to you. Based on how many of you are coming back to the webinars each month, I'm going to assume that they are of value, and again, we thank you. But enough of that. Let's move on to our questions and answers.